Howdy y'alls, it's the Diabolic VTutor, and we're going to be covering the log functions graphing. So that's going to be fun times. Alright, here we are. We are talking about graphing the log function. So basically everything that you've learned about graphing so far, in terms of the shifting rules, they're all coming back. So make sure you remember those things. We're talking about translations, like 3 spaces upwards, or 3 spaces downwards, or 5 spaces to the left, or 3 spaces to the right. We'll go over those in more detail, but those are the ideas that we're going to be hitting upon. So if you already learned how to graph linear functions, that's great. If you've learned how to graph, what are those called? Parabolas? That's even better because those rules are exactly the same thing. So for instance, if we have a function, we're going to call that one f of x. Well, let's call it p of x, p for parabola. So suppose you have a parabola function, and then you have something, it's going to be in vertex form. So we have something like x minus 1 squared, and then plus 5, for example. And then when we see this one, we basically acknowledge that this one has its vertex shifted from the parental position of 0, 0. So we have this thing that is paired up with the x, and then we have this thing outside of the squaring function, which is like the hallmark of our parabolas. And you can memorize some nice... Is it memorizing rules? Yeah, memorizing rules or some associations. So basically, the number that is associated with the x, that tells you the shift left or right, and then the number that's outside of the main function, which is the squaring situation, that one's going to be shifting upwards or downwards. And the funny thing about the number associated with the x is the shift is always opposite of that one. So for example, you see x minus 1. Some people, when they're starting off graphing, they think that it shifts over to the left, but it is not. Because the idea is you're going to be making 0 from whatever's inside the parenthetical associated with the x. So what makes 0 with this x? It's positive 1. So this positive 1 is the true shift, and that shifts rightward 1 space. And then this one is, it looks like what it is. It's plus 5. Basically, all your results get shifted upwards because it's plus 5 spaces. So that was kind of crude. Not my best explanation, but more pertinent to what we're doing. We're talking about the log function. So f of x is equal to something like log of x minus 1 plus 5. And I'm going to put a subscript 2 here. Just ignore that for the moment. So ignoring the fact that this is a log function, it pretty much follows the same rules. So we have a number associated inside the parenthetical with the x. That's inside the quote-unquote main function. And then we have a plus 5 outside of the main log function. So this one is going to be the vertical shift. And it simply shifts upwards because it's plus 5. So the result of the main log function, you increase it by 5, so the y values gets bumped up 5 spaces each. So hence the vertical shift. But this one, again, opposite line inside the parentheticals. We have a minus 1 in the parentheses. So the true shift is 1 space to the right. So right 1 space. Because again, you're thinking about essentially, you're not making 0, but you're thinking about what happens if you do make 0. Alright. And then we need to talk about the log function itself. So before we get to this function in particular, let's talk about the parental function. And then by parental function, I'm going to arbitrarily select log base 2, because that's honestly the easier number to deal with. Better to deal with 2 than to say something like 8. So just dealing with log base 2, but just be aware that there will be some changes. We'll go over those. So at the most basic parental log base 2 function, we're going to have something like this. So again, ignoring this one for a moment, just paying attention to this one. So I do advise memorizing the graph of this function. You don't have to memorize it, but it's definitely better if you do. This is going to be the inverse of your exponential function. So exponential functions, if you recall, or if you've already encountered them, they go something like this. And then this one is just the inverse of that one. So if you sketch out the y is equal to x line, and if we take that and then we reflect this one across this axis of reflection for inverses, you're going to get something like this. If I could draw this properly. Yeah, something like that. And this is basically what we're graphing right there. So that's a quick primer in terms of what function we're dealing with, but there are a few things to make note of, and this carries over from exponential rules if you want to better understand the graph. Again, you don't have to know these things, but it's better if you do, honestly. So for this particular situation, I'm going to sub this out with y. I'm going to drop the parentheticals real quick. So if you recall, for this particular log function, what we can do is we could transform this one into exponential form. So base 2 to the power of y is equal to x. So we could transform this one into something like this, just to talk about it real quick. So when we look at this particular situation, let's just plug in some random numbers and see what happens. So if you plug in x is equal to, let's plug in y. So suppose y is equal to 1. 2 to the power of 1 is just 2. So we get 2. So but you have to kind of read this backwards, because it seems that we chose y first and then we're determining what x is based off the y choice. But I'm going to list it in terms of x first, and then y second. So if x is 2, y is 1. So choosing a different number for the y, what happens? So if y is 2, then x is 4, or vice versa. 4, and then 2. If y is equal to 3, then x is equal to 8. So make note of what's happening. As the x values are increasing, the y values are also increasing. And you notice that the x's increase more rapidly than do the y values at the moment. So that's pretty interesting. Let's just do one more for the road. So if we have something like y is equal to 5, for example, then x will be equal to 32. So again, make note of how rapidly the x's are changing, but then the y ones are just kind of increasing kind of slightly, like by 1, but these ones increase by 2, by 4, and then when this one jumps by 24, this one jumps only by 2. So make note of that. When you get to calculus or whatever, you're going to learn that this is to call this one increasing at a decreasing rate. So even though the y values, the x values are increasing, the y values are also increasing, but they're quote-unquote not kind of keeping pace with the growth rate of the x value. Alright, but that's what the positive values, what happens when we start picking like a 0 or negative values. So if y is equal to 0, 2 to the power of 0 is 1. So check what happens. And if we pick something like -1, for example, then the x value ends up being 1/2. So if x is 1/2, again, we're kind of going backwards, and the y value is -1. And then we could keep doing this. I'm going to do this with a few more numbers. So if this is -2, then x is 1/4. And I'll pick something more extreme like -5, then x value is 1/32. So just keeping track of the trends. As x increases, the y values increase. As the x value decreases, the y value decreases as well. And we make note that the y values are getting negative, but the x values are staying as positive for the moment. But what if is it possible to get negative x values? That is the question. So is it possible to somehow get a negative value for the x? Or rather, if we're inputting a negative value, what would be the corresponding y value? Can we do it? So is there something we can put up here and then somehow get a negative value right there? And from this basic analysis of the trends, it seems not. So we can try to put 0. Nope, we're going to get a positive value for x. We can put positive values. We still get positive values for x. We could put a negative value. But if you recall with fraction tricks or fraction mechanics, this one simply transforms into 1 over positive 2 to the power of 100. So negative exponents, they don't force a negative onto the base number. They just simply invert it into a fraction, and that fraction becomes very, very tiny. Well, what if we put in like fractional numbers, right? So we've tried 0, we tried positive numbers, whole numbers, we tried negative whole numbers, negative integers. But what if we try like a negative fraction? And it's still going to be the same thing. Using exponential rules, we could just send this across the fraction bar, thereby getting 2 to the power of 1/2. But this is still a positive number. So from this very basic analysis, we can see that we can never get a negative value for the x. So this is impossible. At least with this base parental function, right? So with this one, no matter what we do, we can never get a negative value for this one. So in summary, we're working with this parental function. We transformed it into this form just to make the math a little easier to pay attention to. We looked at the data table. It seems impossible to get a negative for the x value. Or if you flip that idea around, it's impossible to put a negative value into there. So if you put a negative value, this is not going to evaluate into anything. So this is called an invalid input. Also known as it's not within the domain of the function. If you try to put this value, if you try to put a negative value into the log base 2 function, it's not going to work. Because by these mechanics, it's not achievable to get a negative, at least for the input, for the x value. So that's it. That's kind of fun. And then the other idea to look at is 0. So is it possible to put a 0 into this particular function? So can we, instead of trying to achieve a negative for the x value, can we somehow get a 0 for the x value? So what does that mean for us? Can we play around with this exponent and somehow force the 0 right here? So just by looking at the trends, if you put a greater x value, you get a greater y value. So that's not what we're trying to achieve. We're trying to get x values equal to 0, right? So if you input higher y values, you get higher x values. So that doesn't make any sense. If we try to put a 0 for the y, we get 1, which is not 0. But when we start putting negative values for y, look what happens. The x values are shrinking, right? So this is a negative 1 for the y value, and we get a 1/2. And when we put a negative 5, we get a smaller x value. So as we are decreasing the y value, the x value also decreases. So it might seem like we might be able to get something very small for x. So what if we put like negative 1,000? Following exponential rules, the x value has to be 1 over 2 to the power of 1,000. So that's a very small number, but it's not 0. But we can try a little bit more. Try a little bit more, right? So we could try 1 million. But once we do that, you still have 1 over a positive value. So this one, it's not quite 0 still. Still not 0. So you could see that we could keep playing this game over and over. So we could keep putting a larger size negative value. But no matter what, there will always be something on the bottom and a clean 1 on the top. And that is never going to be 0. So, which brings us to a basic concept of limits. As we increase the size of this exponent underneath the fraction bar, we can never truly get 0. But we can get something that's very, very small. And we can keep doing it as we increase the negative size of the y value. We're going to get a smaller x value. But it will be impossible to truly achieve a 0 value for the x. I hope that makes sense. But the emphasis of the day is just to do the graphing, so we're going to get straight to the graphing. So what I'm trying to say with this idea is basically there's a limitation to what we can do in terms of the values that we can input into this log function. So in summary, if we're working with this very basic parental log base 2 function, there are some values that we can put into this function for x. We can put positive values. We can put positive fractional values. But we can't put 0, and then we can't put negative values. Why not? Because again, it's impossible to get the y values if we do the analysis. Just to show a quick example again. And we're going to keep it in this particular form just to show something. So can we put a negative in here? So for example, can we put -1 into our log function? So I'll rename that as y. So if x is going to be negative, then we can transform this one. This is basically base 2. And when the rule is, if you take this base and you raise it to the y power, we're supposed to get this -1. So is this possible? And then you could try this out yourself. If you put positive values, no, you're not going to get a negative for the coefficient. If you put 0, you still can't get negative. It's going to be 1. If you try to put a negative value, you just get a positive fraction. And you can keep playing this game, but eventually you're just going to have to give up because you can never get a negative value. At least, again, from this very basic parental function. Later on, if you do a -10, for example, then you can do it, but you still can't put a negative value into there. So we can summarize this by talking about something called the domain of the function. So this, all the values that we can put in x, all positive values are valid. So you can say x, whatever x value you choose, it has to be greater than 0 for the most basic parental function. And that's it. We call this one the domain. And then of course you could learn some fancy smancy notations. So you could say domain x such that x is a value that's greater than 0. Inside these funky curly brackets if you wish. So I don't particularly care. It depends on your teacher. So DOT depends on teacher. I'm gonna be lazy. I'm just gonna do this notation. So that's the domain of the function. Again, those are the valid inputs you can put into this x for this very basic parental function. You can't put in negatives and you can't put in 0. So that's concerning the x input values. And then there's something called the range. This is the values that you can get out of your function. So for any x values that you put into your function, what are the types of outputs you can get? And the short answer is you can get any values. I wish I hadn't deleted the previous work, right? So the range for this particular function is y such that y is any real number. And we could just basically do the analysis yet again. So I'm going to transform this one yet again. It's going to be 2 to the power of y is equal to x. So this transformation is just to make the analysis easier. So check it out. So I'm just going to populate this chart yet again. So if we have a negative value for the y, for example, then this one's going to be positive 1 over 32. If we choose a negative 1/2, for example, this one becomes negative 1/2, then this one is going to become 1 over square root of 2. If y value is 0, x value is 1. If y value is 2, x value is 4. If y value is 6, x value is 64. And we can keep doing this as much as we wish, or we can head in the quote-unquote other direction. So pay attention to the number trends. So you can see that the y value, the x values trends towards 0. These numbers getting smaller. You could keep trying to increase the negative size of the y values. Again, you could do like negative 1 million. But the result for the y is still going to be greater than 0, but it's still a positive value. But you can see that you could pick any value you wish for the y value. So that's what it means when we're talking about this with all real numbers. It means that the y value can be less than 0. Any number less than 0. Again, you could kind of see the trending right here. And you could keep plugging examples until you're exhausted. But trust in the trend, right? So you can just keep plugging in more numbers. Negative 10, negative 20, negative 1,000, negative 1 million. You'll see that the x values get smaller and smaller. So that's one half of this idea. Can we plug in 0? Yes, we can. So if the y value is 0, again, x value just becomes 1. So this is valid. Any negative values for the y is valid. The 0 value for y is also valid. And then if we plug in positive y values, the x values just increase over and over. So you can plug in 100. You're going to get a big positive x value. You can plug in 1,000. You will get a larger x value. And you can just keep doing this. So can we plug in values for y that are greater than 0? Yes, we can. So all three of these ideas, y value could be greater than 0, y value could be less than 0, or y could be equal to 0. That's what we call the range is all real numbers. So I kind of flipped it backwards, right? Because I'm saying if we put in y values, but you have to flip it on its head and say the x values will get you what y values. So flip it around. So if you plug in a tiny value for x, you get a negative value of y. So negative values of y's are achievable. If we plug in 1 for x, we get y0. If you plug in larger positive values of x, you get larger positive values for y. So that's how we can think about it. So in summary, what are the range of values we can get out of this function for the x values that we choose? We can get negative y values. We can get 0 for the y value. We could get y positive values. So thus, the range is all real numbers. So those two ideas. And then we're going to expand a little bit more on these ideas. Actually, let's do it right now. So based off this number trend, if you feel like this trending pattern is not enough data, you could always plug in more values yourself, or you can verify this on the graphing calculator. It's not a perfect proof, of course. You need higher mathematics. I would need higher mathematics, but just based off of the number trends, as the x values decrease, as you're picking smaller and smaller x values, the y values are also decreasing. And we could summarize this. So we can't pick 0. Again, going back to one of our earlier ideas, if you plug in 0 here, it's unachievable because 2 to the power of something will never get you 0. So we can only creep closer to 0 for the domain. So expanding upon this domain idea, we could say something like this. As x approaches 0. This means that we are plugging in values of x starting from 1 to 1 over root 2 to 1 over 32, for example. And we could pick x values that are creeping closer and closer to 0. But we have to pick positive values. So this is x approaches 0, but still x is still a positive value. So we could pick something like 0.001. But again, we can't pick 0, and we can't pick negative values. Because if we pick a negative value, that's impossible to achieve, because 2 to the power of a y value, some value that you choose, no matter what you think about, you can't get a negative. So as we pick x values that are approaching 0, but they're still positive values, the y values are shrinking forever. So first we started with a negative 1/2, then we get negative 5. You can imagine that as we pick smaller and smaller x values, like 1 over 1 million, for example, that's going to result in a very large sized negative y value. And we can summarize this trending pattern. So as x approaches 0 from the positive side, y approaches negative infinity. So don't just simply trust me on this. You should verify this on the calculator yourself if you have time. You could sit there and plot the data points, but it's a lot easier if you check out the visual graph. What's going to happen is on the visual for the graph, if you look at it, it's going to look something like this. So as you pick, for example, if you pick this small x value, the corresponding y value is negative right there. If you pick this x value, the corresponding y value for the function is right there. If you pick this smaller x value, the corresponding y value is like way down here. That's a larger sized negative value. And we could keep playing this game over and over. So rather than picking this small positive x value that's getting closer to 0, you can pick this one that's even closer to 0. You're going to get a larger sized negative y value. Can't pick 0. But we could always continually pick smaller and smaller x values, leading to larger sized negative y values. So this is what that one is talking about. This one is just summarizing the idea of picking smaller and smaller x values and achieving smaller and smaller y values. And that's it for that particular something. This is called an end behavior. Kind of a weird name because this one never ends. But we're talking about the trending pattern if we can go on by plugging in smaller and smaller x values. So the end behavior of this one, this is called an end behavior. If you symbolically draw, if you draw an arrow, you are symbolically representing the fact that there is a trending pattern, but the trending pattern goes on forever. So, end behavior. And this one describes that particular end behavior right here. And of course, there's another side to this graph. This is the other arrow end of the graph. The arrow goes on forever. Why did we say that? Because we're saying we could arbitrarily choose larger and larger x values, and we will keep getting y values. In fact, we can quote-unquote get all the y values, quote-unquote. So right here, it's going to be the same idea, at least pretty much. So if you pick this positive x value, then the y value that corresponds to is right there. If you pick another x value, that y value is greater than the previous y value. And you can keep picking larger and larger x values. And if you pick larger and larger x values, the corresponding y values are also increasing. So as x values increase, as you pick larger and larger x values, the y values also get larger. And we could summarize it using this funky notation. As x approaches positive infinity, then y approaches positive infinity. Again, it's not truly verification, but you can see the trending patterns if you plot the function, if you check the data table, if you check the visual of the graph will keep going in a diagonal upwards, rightwards, and upwards fashion, and you can keep going no matter how far up the graph you creep along, it will keep going up. But it does increase at a decreasing rate, however, but you don't need to worry about that. And unfortunately, that's a lot of blabbage. But that's what you get when we're talking about end behavior. So this is end behavior number 1 as x approaches the end of the domain. And the other one, as x approaches a larger and larger positive values, y values also approach positive values. But since we're talking about f of x, call that one f of x, just to keep good form. Call that f of x, please. Don't call it y. F of x. So just from these ideas, we're just talking about how the graph overall looks. So there's an arrow going down, and then there's an arrow going up. That's it. So this one is that one, and then this one is that one. And this right here, the 0 right here, that's kind of a wall for our function. That's the wall for the function. And the function, the graph of the function will never break past that wall, because again, you can't plug in negative values and you can't plug in 0. And this wall is a familiar idea. It's called the vertical asymptote. We've seen this in graphing fractional rational functions. What are those called? It's like when we have a polynomial over another polynomial, then we have vertical asymptotes for those ones. So this is a wall, and this wall is located as x is equal to 0. We can't make x equal to 0, but for this visual representation of the wall, we say x equals 0. Again, that's the VA. And again, this arrow here, it goes onwards and upwards forever. But that looks ugly, so I'm not going to draw like that. Okay, so we have the main idea of how this graph looks. Again, that's only for this one. Later on, we're going to get to what if we have a negative value, and what if we have a negative modifier on the x, or what if we have a negative value on the outside. So once you get this down, or if you just simply memorize this one, then all you need to do is just apply the shifting rules. But there's a few more things we need to talk about. And I call them anchor points. I don't know what else other people call them. But there are some very nice values you can pick that will make your graphing very easy. And if you know where to put these points, your shifting rules will be very easy. So you see how this is base 2? When we're deciding to pick anchor points, always pick variations of this 2. And by variations, I mean like exponents of 2's. So if you take 2 to the power of 1, for example, it's going to be 2. Which means this. In choosing to plot perfect points, you pick exponents of that one. So 2 is a very good one. 4 is a good one. Not 6, because 6 is not an exponent that you can achieve by putting a nice exponent for 2. 8 is the next one. 16 kind of pushing it. I wouldn't do 16 because that typically goes off scale for typical graphs. 1 is good. 2 is good. 4 is good. So why 1? Because 2 to the power of 0 equals 1. So those are very nice points. So this one is a very stereotypical anchor point. 2, 2 is good. So 2 to the power of 1 equals 2. Also a nice point. And 4, 1 is also a nice one. So 2 to the power of what equals 4 to the power of 2. So these are very easy to graph. So whatever bottom number this is, always pick the exponent versions of that number. You can also pick the fractional ones like 1/2. So picking the fractionals with the 2 on the bottom, or 4 on the bottom, or 8 on the bottom. So 1/4 or 1/8. So 1/4 is perfect because 2 to the power of -2. So something like this, and then you get 1/8. So 2 to the power of -3. So very nice ones. But you could stick with the positive ones, honestly. So we haven't even begun to graph it yet. But in picking nice points, again, we want to pick the very optimal points. So what is this when y value is 0? 2 to the power of 0 is 1. So this is one of those crucial anchor points, 1, 0. Next one up is 2 to the power of 1 is equal to 2. So 2, comma, 1. 2, 1. Well, this graph is kind of funky. Honestly, I think picking 2 points is ample, but depends on teacher. Some teachers will require you to put more points. Alright, and then of course if you have shifting rules, all we need to do is move those anchor points upwards or downwards. And then you're going to see the interplay. So for the most part, when we're graphing these type of functions, I would say you would have to find the wall, find the vertical asymptotes, find the anchor points, and then just shift them accordingly along with the walls, which sounds kind of abstract. But we'll do some problems. So let's start with this basic one. We could sit there and plot points, but let's not plot points, because that's kind of a hassle. Okay, so here we go. So all we need to do is just do the domain considerations and then the range. Range is pretty boring. It's always all real numbers for this log type functions for aforementioned reasons, right? Alright, so first domain considerations. So what can we put into here? Now remember, as a whole, whatever we put in here, it can't be 0. Can't be negative. Now there's a very easy way to set that up. So all we have to do is take this x minus 1, and we say to ourselves, it always has to be greater than 0. And then you solve for x. Plus 1 plus 1. No matter what we put into here, no matter what we put into the x values, whatever we put in must be greater than 1. Again, technically this is sloppy notation, but that's not my focus. So if you try to put 0, for example, we can't do it, because if you put 0, 0 minus 1 is negative. And we can't have negative inputs inside our log functions as a whole. So the domain is finished, and then the range one is fairly boring. Log functions, you can achieve negative outputs. We can achieve positive outputs. We can achieve 0 outputs. Check the number trends if you wish. So this one, very basic. Always put all the numbers. And then we make note, this is a very basic log function, log base 2 function. There is no negative on the x. and there's no negative right here. So this one follows standard parental function movement. It's just this situation. So down, up. So from the prior discussion, what can we talk about this one? As x approaches, as we pick larger and larger x values, then the resulting y values also get larger. So that is summarizing this end behavior. So as x values increase, y values increase. So just a quick reiteration. If you pick this tiny x value, you get the small y value. If you pick this x value, you get a bigger y value. If you pick this x value, you get a slightly bigger y value. And we can keep playing this game because this graph goes onwards forever. So, for example, if you pick this bigger x value, you get this bigger y value. This y value up here is greater than this y value there, summarized in this statement. And of course, if we pick in the other direction, as the x values get smaller, as we pick smaller and smaller x values, well, there are certain restrictions for what x values we can pick. According to our prior statement about domain function, the x values, whatever x values we choose, have to be greater than 1. So we can't pick 1, but we can pick values close to 1. So we can say as x approaches, as we pick x values closer to 1. But we have to pick positive values, so plus. Because again, you can pick something like 1.1, and that's okay. But you can't pick 1 exactly, and you can't pick 0.9. Because this results in negative. So as we pick x values that are closer to 1, but still positive, still greater than 1 in size, then the y outputs approach negative values. And you could trust me on this, or not trust me on this. Check this out yourself. As you pick smaller and smaller x values, but staying within domain restrictions, the y values approach negative infinity. They get smaller and smaller and smaller. Please look at the data table. All right. So domain, range, and behaviors for this f of x function. So we're almost done though. It's kind of annoying. So it is what it is. X value is greater than 1. This one dictates the wall. So if x has to be greater than 1, then our wall is at x is equal to 1. So x can't be 1, but our vertical asymptote is at 1. It's the wall that's stopping us. The wall. All right. What else do we need to cover for this one? Oh, the anchor points, right? So here's how we choose the anchor points to begin sketching out our graph. Well, we already have the wall. That's already good. So in terms of anchoring points, make sure you pick values of 2. So it's nice if we can get this whole thing to be 1, to be 2, or to be 4. Those are the nice ones. We can also get 1/2. So pick very easy numbers. The 4 one is probably a little extra, so we don't need the 4. These two honestly are probably enough. So the question is, how can we get this whole thing to be 2? Just do algebra. X minus 2, x minus 1 is equal to 2. So therefore x is equal to 3. So if x is 3, 3 minus 1 is 2. 2 to the power of what gives us 2? The y value has to be 1. So hence, if x value is 3, then y value is 1. So we already forced this whole thing to be 2, right? So we can force this whole thing to be 1. How do we do that? X minus 1, force it to be 1. X is going to be equal to 2. So if x value is 2, we can force this whole thing to be 1. 2 to the power of what is equal to 1? It's 0. So we're being very deliberate in the x values we are choosing. So 2 points are sufficient for my purposes, honestly. But again, depending on teacher, you may have to do more. So again, 2 to the power of 0 equals 1. Those are the anchor points. Technically, the shifting rule has already, the shifts have already been taken into account because of our setup. We already took into account this -1. So, plot it as is. So x value is 1, 2. We get y value 0. X value is 3, 1, 2, 3. Then the y value is 1. And the graphs will almost always proceed in the same fashion. Again, especially because we don't have a negative here, nor a negative there. So this follows standard curve behavior like this one. We've already summarized it right here. So as we pick smaller and smaller x values, getting closer to 1, the y values explode downwards, like so. That's this one. And as we pick larger sized x values that are positive, y values also get bigger. So as we pick larger and larger x values, the y values get bigger. So, like this. And then, this is where it gets kind of artsy-fartsy. We need to connect this graph because the domain is x values greater than 1. So we need to connect this graph together. Just connect it as smoothly as possible. Like that. So don't do something funky like this. Don't do that. Just do that. You could always check the data table for that. Alright. And that's essentially how we graph the function. It's a lot, honestly. It's a lot to consider. It's a lot of steps, and depending on teacher, you may be required to list all your steps. You might have to do a full analysis table. You might have to do this end behavior summary, domain and range summary, and then you might have to pick a couple of anchor points. You have to state the vertical asymptote and all that fun stuff. But essentially, this is what you have to do. So I'm definitely going a lot slower now, but once we get to more and more problems, I'm going to stop trying to explain it. Well, I'm not really explaining everything, but I'll stop rambling on so much. Hopefully. Alright, looking at the next one, let's talk about g of x. Now we're going to do something a little funky. It'll be x plus 2. Now this is going to be base 3, not base 2 anymore, log base 3. But our considerations are still the same thing. And depending on how you want to operate, let's do domain range first. So domain considerations, what x values can we put into here? Well, we can't put in 0 and we can't put in negative. So this whole thing has to be greater than 0. So we force it. X plus 2 has to, as a result, must be greater than 0. So x is greater than negative 2. That will be our domain. And then you might have a question about, wait a minute, I thought you said inputs can't be negative, right? I mean inputs as a whole. So if you put something like -1, for example, for the x, what results is, because we're increasing it by 2, the entire result as a whole is positive, and that's okay. So I've always stated that the input as a whole has to result in a positive value. It has to be greater than 0, has to be positive. So if you put exactly -2, the sum of which is going to get you 0 as a whole, and this is the one we can't have. So that's the domain consideration, and then the range, it's standard, it's very boring. All the numbers, at least for our log functions. So that's typically the starting analysis, and then we get to the end behavior analysis. Make note that this x is positive, and then this is also positive, invisible +1 in the front. So our graph is going to do the boring standard movement. Negative right there, positive right there. So we talk about that. So as x approaches larger and larger size positive values, the g of x approaches larger and larger positive values. Again, you could always verify this. But this one, I'm going off of how the parental function operates. This one is not, there are no reflections from the parental function. Again, no negative, no negative. So it does the very boring standard parental motif summarized here. That's why you have to memorize some things about your graph. And then the other behavior, we can't do this. Domain restrictions. But what can we do? We can't plug in -2, but we can get close to -2. So don't put -infinity, -2. What happens when our x value approaches -2? Again, standard parental movement. Y values approach -infinity. This one here is describing that behavior. As we pick smaller and smaller x values getting closer to -2, the y values explode downwards. And if you don't trust me, as you shouldn't, check the data table. And thus we have the end behaviors. Alright, perfect. And then next up, let's make sure to state the domain, the vertical asymptote, which you could just take it straight from the domain that we've already specified. So x has to be greater than -2, so x cannot be -2. We take this one, and that's going to be our vertical asymptote. That's the wall. We can never pass this wall. We can never cross this wall. Never ever cross vertical asymptotes. And that should be enough for... Oh no, we still need the anchor points. Yep, anchor points. So anchor points, this is now base 3, not base 2. So the optimal thing to force this entire argument as a whole, we can force it to be 1 and force it to be 3. So how can we force 1 from this one? So x plus 2, we force it to be 1, and then x plus 2, we're going to force it to be 3. So what does x have to be? -1. So if we force x to be -1, this whole thing is 1. 3 to the power of what? Gives us 1. It's 0. So this anchoring point is on our graph for sure. Next one. We're forcing 3. In order for the total result, in order for the total argument to be 3, what does x have to be? It has to be 1. So if x is 1, 1 plus 2 is 3. 3 to the power of what? Equals 3. Has to be 1. So again, if x is 1, we force the 3 argument, and then the y value ends up being 1. And thus we have our anchor points. Just take that, and we'll just plop it right here. So I chose 2 points. Your teacher may require 3 or 4. Who knows? Or you should know, I mean. And now we just gotta populate the graph with all the information we've gathered. So I like to put the wall first. You could get it straight from here, right? Wait, I should delete this. Okay, so we have a wall here. X is equal to -2. That's the vertical asymptote. X for the function can't be -2. So find -2. -1, -2. That's the VA. I'm color coding it in red because it can't be 2. It can't be -2. And then take our anchor points. We have one at -1, 0. So right there. And then we have another one at 1, 1. And then following the end behaviors. As x grows larger, y values also grow larger. So that's going to be onwards is upwards. As the x values get smaller and creep closer and closer to -2, the y values explode negatively downwards. As x values get closer to -2, the y values explode downwards. Now comes the artsy-fartsy part, connect it as smoothly as possible. We're good. It's a little too sharp right here, honestly, but that's what we get with hand-drawn graphs. Let me try to beautify it just a little bit. Okay. There we go. Well, that's still too sharp. There we go. And that's it. We've successfully graphed the function given right there. So again, we can have negative x inputs, but the whole result after any modifications cannot be negative or 0. It has to be greater than 0. So that's just talking about the domain, and then the range is very boring. It's all real numbers. And behaviors, base it off of the parental function. I do recommend memorizing it, but you could always do data table, but that takes a little bit of time. Anchor points, learn to pick the optimal points, and that's based off of the base. Pick exponentials of 3. Alright, next up. Alright, next up we have f of x. Let's do h of x. So still no negative signs in front yet. Pick a log base 4. And then now we'll put like a -1 out here. So make note, this is still positive, and then this is still positive. So it's going to follow the standard boring movement of downwards, upwards like this. Because this one right here matches the overall behavior of this one. We'll talk about reflections afterwards. Maybe the next problem, but here we go. Talking about domain issues, we force this one to be greater than 0. Because you can't have 0 arguments or negative arguments as a whole. minus 3, minus 3. X has to be greater than negative 3. Range is boring, all real numbers. Check the data table. So you can see how this can eventually become clockwork. And again, positive in front of the X. So it follows this kind of trend. As X approaches positive infinity, the Y value, or h of X, approaches positive infinity. As the X values get closer to what? The wall, which is at negative 3. So as X approaches the vertical asymptote negative 3, the Y value should explode downwards. And behaviors. I'll put a U for you British people. There you go. Alright. And of course, summarize the wall. Just kind of extract it straight from the domain restriction. So X has to be greater than negative 1. So X cannot be, I'm sorry, negative 1, negative 3. Then that means X cannot be negative 3. So that's the VA. Now we pick the anchor points. This is base 4, so you force this to be 1 or 4 as a whole. So how do we force this one to be a 1? If X is equal to negative 2. Then this whole thing becomes 1. 4 to the power of 0. 4 to the power of 0 gives us 1. So we know this is our point. This is one anchoring point. Again, not positive 1. That's not our anchor point. That's not the X value. This is the X value that gets us 1 as a whole. And that corresponds to a Y value of 0. 4 to the power of 0 is equal to 1. Negative 2 plus 3 is the one we desire. Anchor point number 1. Next one up is 4. How do we achieve 4 if X value is 1? So 4 to the power of what gives us 4 as a whole? 4 to the power of 1. Feel familiar? It should. So there are anchor points. Put it right here. So at this point we have enough to sketch out the rough graph. Place the wall at negative 3. Please do dashed lines. VA, where is our wall? Our wall is X, is the wall is at negative 3. Anchor point number 1. Anchor point number 2. In behavior nonsense, as X grows, Y grows. As X gets smaller, closer to negative 3, Y values explode downwards. Connect these two as smoothly as possible. That's a little too sharp, but that's okay. That's good enough. And that's basically the graph for this one. Now let's do reflections. And in order to talk about reflections, let's just show a few examples first. in terms of what happens when we have negatives in the inside or on the outside in regards to this standard parental function, log base 2 of x. I'm going to just call this y for now. So what happens? So this one, standard parental function, like that one. Okay, so let's just talk about the transformations. What if we have a negative value right there? So this is going back to, if you remember your reflection rules for quadratics, it's going to come in handy right here. But if you don't have much of a, if you haven't had much experience with the parabolas, graphing parabolas, that's okay. This negative here, make sure you make note of where it's happening. This negative here is being applied after the main log function. So you take care of the log function first, and whatever output you get, it's turned into a negative. It's flipped. So this, whatever you get, you could think about that as the output or the y. This is the unmodified y, and then we make a negative. So what that means is if this is the parental function, if you inputted a positive x value, you get this positive y value, right? That's the standard parental function. But now, if you put the same x value into this reflected function, you get the same size y value, but it's negative. Right there. Now let me just put a concrete value for the parental function. If you put 4, then we get 2. So if you put 4, then you get positive 2. But for this reflected version of the parental function, if you input a positive 4, then we get what? A negative 2. Wait, what am I saying? Yeah, we get a negative 2. Because whatever I'm isolating here, ignore the negative sign for a moment. 2 to the power of what gives us 4? 2 to the power of 2 has to give us 4, right? But we have this negative, so this one becomes negative 2. So if we try to put positive 4, we don't get positive 2 as before. It's modified with the negative in front, which is why we get negative 2. Again, that's what this particular function right there. And we could just keep doing this trend, basically. You could pick 8, for example, but whatever's inside the rectangle, ignoring this negative sign for a moment, if you have 2 to the power of 8, then this whole thing is going to be 3. But it gets modified afterwards, after you apply the log function. It's modified with a negative value. So it's negative 3. So if x is positive 8, then the output, you put the negative modifier onto the 3, so negative 3. So 8, negative 3. And that kind of leads to something interesting. So instead of having the standard parental upwards trajectory function, we actually get an inverted or a flipped function. That's this one. So long story short, if you have a negative outside of the log function, all you have to do is reflect it across a horizontal axis of reflection, and it becomes starts upwards, goes downwards. And to summarize that end behavior, as x approaches the wall, A for the wall, no, I'll put 0 in this case, it's just 0. So x approaches 0 from the positive side. The y value approaches upwards, positive infinity. And then as x grows larger and larger, y values approach negative infinity. So from those two, the range is still all real numbers. But this one, actually no, not but. So the range is still pretty much the same thing. I mean, the domain is still pretty much the same idea. Whatever x values we pick in here, x has to be greater than 0. I hope that's clear. So going back to standard parental function. Transform. I'll call it y again. So we've just talked about what happens when we have a negative out in front. Basically, the log function applies first, and then all the results become negative. So that's why there's a reflection. In this case, this is untranslated, so there's a reflection across the horizontal axis. But what if we don't have a negative up there? What if we have just positive log base 2 and now negative on the x? So when we have a negative on the x, that basically means all of our inputs have been inverted. So before, for the parental function right here, we could only put in values that are positive. But now that we flipped it, we can now only put in negative values. But the setup is still the same as before. So you take this one, has to be greater than 0 as a whole. So this is a negative. We can add x to both sides, so plus x for the manipulation. So it becomes 0. It becomes x. So x has to be less than 0. So what has happened? If you have a negative inside the function, that flips all of your input values. So our domain gets flipped. Not the y values, it's the x values that get flipped. So what that means is going from the parental function, the graph of which just looks like this. So, but when we get to here, we can't have positive x values anymore. We have to have negative x values. So the graph gets reflected across the vertical. So it becomes something like this. Because we can put in negative 10, for example. So we put negative 10 as a direct x input. This negative here cancels with that negative, thereby giving us positive input. And that's okay as an argument as a whole. But if you try to put in something like a positive 20, for example, no, like positive 16, for example, it doesn't work anymore because now it's a negative 16, and log functions can take in negative arguments as a whole. So that will fail. Summarized here. So all that did was, if you have a negative inside, it just reflects your graph across this vertical, if it's unshifted. All right. And then comes the last situation, of course, when we have a combination of the two. So that's the parental function. this is positive and this is positive. But what if we have, for the parental function modified, what if the argument is negative and the result is negative? And that just means we need to do the reflection twice. So all you need to do is apply the two prior ideas twice. So this one reflects across the vertical. This one reflects across the horizontal. So looking at the parental function yet again. Positive, positive. That one's just gonna, this one just looks like this. Downwards, upwards. Take into account this negative transformation. It's going to get reflected across the vertical. Now we take into account this negative on the outside. All the y values get flipped. So instead of having, for example, a positive y value here, it ends up being down there. So like this. So what are the end behaviors as x values approach the wall? Y values shoot up. Oh, I'm sorry, this is not the wall. Whoops. Because the domain has been altered, so we can't approach bigger and bigger x values. We can only approach the wall. Now we're approaching it from the smaller side, from the negative side, so don't put plus here. We can put minus. What's happening right there? As x values get smaller and smaller, what happens to our y values? The y values also get smaller. And thus we can summarize the end behaviors like this. For you British people. So putting those two reflections, we get this result of end behaviors. And do you have to memorize it? No. If you could draw this picture mentally in your mind's eye, that's very useful, but you can always draw it out if you really want to. So in summary, if you have a negative inside there, that reflects across the vertical. If you have a negative out there, it reflects across the horizontal. And now let's just put those to do some graphing problems. So here we are. We're going back to f of x. Negative so something fairly simple. Let's make this base 3. So same strategies as before. We just make note that there's now a negative outside of the main log function, so we know that the y values get flipped. There's a positive on the input, so no reflections across the vertical. So we only have one type of reflection, and it's going to be that one, across the horizontal. Same analysis before, domain, range. But this one we consider that it has been reflected. Domain, not so much. Standard situation, x, we're going to force it to be x minus 1 as a whole to be greater than 0. So therefore x is greater than 1. That's our domain. We could make note of the vertical asymptote right away. Since x is greater than 1, then that means x cannot be positive 1. Can't be positive 1. That means the vertical asymptote is x is 1. Again, we have this negative out there. And that means that we don't have the standard parental function movement anymore. It's going to be negative, so reflect across the horizontal. So downwards. so downwards. But, you know, we can keep this boring. We can just say all real numbers. But now we need to talk about the end behaviors. End behaviors, as x approaches larger and larger positive values, the x values, as x approaches positive and positive larger values, what happens to the y values? Then the y values, more and more negative. What happens when x approaches negative infinity? It can't, because we have a wall at 1. So we can't approach negative infinity, we can only approach the wall. So what happens when x approaches the wall? When the y values approach, follow the sketch, it goes upwards forever. So positive infinity. And thus we have our end behaviors encapsulated here. What else do we need? We need the anchoring points. So let's just pick very nice values. So this is base 3, so we can force it to be 1, we can force it to be 3. In order to force 1, this x has to be 2. Because again, 2 minus 1 is equal to 1. So 3 to the power of what gives us 1? 3 to the power of, the y value has to be 0. So that's anchor point number 1. Anchor point number 2, we want to force this entire inside to be 3, which requires, so if we force this entire inside to be equal to 3, that necessitates that x is 4, because 4 minus 1 is 3. So 3 to the power of what gives us 4? It has to be, I'm sorry, not 4, 3. 3 to the power of what gives us 3? It has to be 1, so this needs to be 1. But don't forget, we need to take into consideration the negative. Okay? So let's backtrack just a little bit, just to make this clear. Absolutely clear as possible. Again. Oh, hi, we have someone in chat. How do I type in chat? Hold on. Well, I see ya. Well, unfortunately, this is just like the early on tutorials, but we're going to pick up the speed. Hold on, let me try to type something in chat real quick. Alright, so we're talking about this one right here. We're talking about the f of x function. We are currently on the negative situation. What happens when you have a negative value on the log function? So strictly reflections. Where were we? We already finished talking about the end behaviors. We're just picking the anchoring points at this point in time. So again, we want the entire inside here to be 1. But this is a negative, and that's okay, because 3 to the power of 0 is going to give us what situation, right? So that's what we're considering. How do we force this entire thing to be 1? Well, actually, that's kind of weird, because we want... Wait, how do we talk about this? Okay. So we want this entire inside to be 1. And that requires the x is 2. So if x is 2... then what happens? Unfortunately, it becomes negative as a whole, right? So negative 1. What am I saying? I forgot what I was saying. Okay, well, let's backtrack just a little bit. 3 to the power of 0, we definitely want 0. Because that's going to give us... Let's consider this for a moment. So 3 to the power of 0 will give us 1, right? And then we want this whole thing to be 1, so the result of this whole thing must give us negative. Wait, why is this so confusing? That's a reflection over the y-axis and the horizontal translation 1. Yeah, that is correct. Horizontal movement 1 space to the right, and then we have a reflection across the y-axis. Yes. That's exactly what's happening. But at the moment, I'm just trying to come up with the good anchoring point. But my brain is failing me at the moment for some reason. I'm trying to summarize this very methodically, but at the moment, again, like I said, my brain is just failing. So again, we want this to be a 2 because 2 minus 1 is going to give us 0. So that's what is going to give us 1 as an argument, which is perfect. Because if you have a log of 3 of 1, and then this is negative, then this whole thing is... What is that? That just sounds very weird to me. 3 to the power... I think that's fine, right? Wait. Okay, hold on. I'm going to take a quick pause. 0, 0, and 2, negative 1. Yeah, because of the negative. Okay, yeah, I think that's... Yeah, I don't know. I'm having difficulty summarizing it because I'm trying to state it in a regular fashion, but you are correct. Yes. So if we force the entire argument to be 1, that necessitates that the x value is 2. So yes, you're correct. It's going to be 2. And then just having difficulty talking about the negative sign. So normally, if we ignored this negative, then this one would be positive 1, right? But since we do have that negative, it forces this one to be negative 1. So yes, you're correct. It's 2, comma, negative 1. And that's good. So this could be anchor point number 1 in order to have a easier time sketching the function, the graph of the function. And then the other one that you picked was 0, 0. Let me erase this real quick. So if you pick 0, that means that you're forcing the inside to be negative 1, which is perfectly fine. That's definitely a valid anchor point that you can pick. So if your x value you're forcing is 0, then basically what happens? So if we force 0 as an input, this whole thing becomes negative 1, and then we do have a negative. So 3 to the power of what gives us what? Wait, we can't have negative 1. No, we can't have 0, 0 for this particular function. Here, I don't know if you saw it, but here's the original function. So for our domain restrictions, x has to be greater than 1. So we can't pick 0 for the input. Yeah. But if you mean... What do we mean? So we can't force the entirety to be 0 because we can't take log of a 0. But we can force the entire thing to be 3 because 3 will match 3. We already forced a situation where we make this inside part 1 as a whole. So I think the next easiest anchor point is to force the entire thing to be 3, which necessitates this as 4. So if x value is 4, then 4 minus 1 is 3, and we can take log base 3 of 3. That's just going to give us 1, right? But that will give us negative. Wait, that can't match the previous one. I'm going to have to check the previous one. Hold on. So this one should be correct. Again, if you pick x is equal to 4, 4 minus 1 is 3, and then log base 3 of 3 is a familiar friend. That's just 1, but we have a negative in front, so it's negative 1. So that is a good anchoring point. And just to fix up the prior anchor point, this one is incorrect. So in consideration of the previous thing, we tried to force this whole thing to be 1. And that necessitates that x is equal to 2. So we'll just evaluate it. So if x is 2, 2 minus 1 is 1. Log base 3 of 1 is 0. We have a negative 0, so it's just going to be 0 as an output. So this will be anchor point number 1, and that's anchor point number 2. So 4, negative 1, and then we have 2, comma 0. So do we have enough to graph the situation? Yes, we do. So we have the wall, we have the end behaviors, and then we have the 2 anchor points. So let's place the wall first. X is positive 1 right here. And then we have 2 anchor points. 2, 0, so this is going to be positive 1, positive 2. And then we have 4, negative 1. So 1, 2, 3, 4, negative 1. Following the end behaviors we already specified. As x increases, the y decreases forever. So onwards is downwards. And then as x approaches the wall, the y values explode positively. So as x approaches the wall, y explodes positively. And then lastly, just beautify it, just connect those two. And then there we go. It looks a little funky. It's kind of a sharp turn right here, but you know, just try to fudge it out. It's good enough. Good enough. So in summary, what has happened? So basically, we just have a negative out there. There's positive x modification. So all we have to do is reflect the parental function, which used to be like this, with a negative on the outside, reflects vertically. So it ends up like that, which describes the end behaviors. We have 2 good anchoring points right here and right here. Your teacher may require more than 2. I don't know. Depends on teacher. And we have the wall at positive 1. So that means we're good to go, and that takes care of this particular problem. And then we'll move on to another situation. Alright, so what do we got? We got g of x is equal to what? 2 minus log base 5 of 3 minus x. So we have multiple annoyances here, right? We have a negative on the x. We have a negative there. So we have 2 flips. We have 2 reflections. So reflection across the vertical, and then reflection across the horizontal. So keep that in mind. So let's start with the domain and range analysis. So if the so just a quick question. So if the equation has negative in front of the log, do you just need to consider the point by adding 1 in the x-intercept, even though it looks like it's being subtracted? Wait, let me think about that question. Yeah, because of the goofy shenanigans in terms of determining the shift. If you have a negative inside the main function parenthetical, then you're shifting in the opposite of the sign, because in essence your x values are ultimately being reduced, which means you need bigger x values. So yes, you shift in the opposite direction. Yeah. So hopefully this example, if I'm understanding what you're asking is correct, yes. So let's look at this one. So have your prediction based off of this one. So if you have a 3 minus the x, what do you think happens for that one? And then we're going to test that hypothesis in a moment. So standard procedures, this is kind of goofy though, because now it's 3 minus x. But you should always manually set it, flip it around yourself. And then just for sake of idea what's happening, there's a reflection. If you factor out the negative, you get the true shift. So be careful with this type of situation. So if you factor the negative out, we get positive x, and then we get negative 3. So the true shift is plus 3 to the right. So right 3 spaces. So be careful. Always, always, always factor out from the x. Always make the x positive, and you'll get the true transformation, and then you get the true shift, which is kind of annoying. This same idea will hold true when you're working with graphing trig functions as well. Technically even parabolas. Okay. So domain restriction, all you have to do is, again, force the inside to be greater than 0. So solving for x plus x to both sides, x values are less than 3. Personally, I don't like to do the goofy flip trick, but if you memorize it, you can use it. So some people like to subtract 3 from both sides, so they get negative x is greater than negative 3, and then they divide both sides by negative, so they get x is related to positive 3. But this is where you need to memorize the goofy sign flip. If you divide an inequality by negatives, you have to flip the sign. And I hate memorizing tiny rules like that. So to avoid that, if you see a negative x, just add x to both sides. And then you can flip this as you wish. There it is. Alright, so that's our domain restriction, and then from the domain restriction you can immediately get the wall, our vertical asymptote. So x has to be less than 3, so x cannot be 3, which means the wall is at 3. There it is. Range is boring, it's just all real numbers. And then there we go, and then we're going to consider the end behaviors for our function. And remember, make note of the negative signs. We have negative on the log, and then we have negative inside the parenthetical, so again we have 2 reflections. So the parental function is like this. So first, we can reflect like that. That's considering this reflection, and then we reflect this one, like that. So that's ultimately what the end behavior is going to look like. This one right here, and then this one right there. Just keep track of the wall. So I should have put the graph like closer. What are our anchor points be 4, 2, and 8, 1? Let me check that out. We're going to do that. Might as well do it right now. Alright, so you're asking if it's 4, 2 or 8, 1. Let's check. So why are you forcing this 4? If you force the 4, it doesn't work because you have 3 minus 4, which means the argument as a whole is negative. So we can't have negative resulting from the argument. Yeah. That's fine. So in terms of picking the anchoring point, right? Check it out. Just base it off of this 5. So what we want is just cover this up for a moment, right? Just cover it up. So you want the entire argument, this whole thing, you need it to become 1, right? Because ultimately, if we have log base 5 of 1, we know this evaluates to 0. And then 2 minus 0 is very easy to do. But how do we force the 1 on the inside? So we just do simple algebra at this point. So we force the 3 minus x to be some number that we really like, which is 1. So plus x minus 1. So x is 2. So if we force x is 2, this whole thing becomes 1. If that whole thing is 1, then this whole log evaluates to 0, and then 2 minus 0 is 2. So thus we have anchor point number 1. If we force x to be 2, then the resulting y value will be 2. So anchor point number 1, 2, 2. So again, that's when we force the entire inside to be 1, because we like working with 1s as a whole inside log functions. And then the next one you pick, we could just pick 5. Since the log base is 5, we can force this entire thing to here to be 5. How do we force the 5? Just set the algebra. So 3 minus x, we want to force the 5. So plus x, minus 5 minus 5, so x is equal to negative 2. So what happens when the x is negative 2 again? You get 2, we get 3 minus 2, which is positive 5. So this whole thing transforms into log 5 of 5. And that's the type of numbers that we like, because we know that evaluates into 1. So when this whole thing becomes 1, it becomes 2 minus 1, which is just 1. And then those will be 2 adequate anchor points. And for my purposes, 2 points are sufficient, but if your teacher requires more, you can force other nice values of 5. So always pick exponents of 5. So we already picked 1. We already picked 5. We can force this entire inside to be the next one, which is 25. It's not my favorite one to do, honestly, because it goes off of the grid. So we could go backwards. So we can force, instead of forcing positive values, we can force fractions, right? We could force 1 over 5. And again, that one's not the nicest situation. So how do we force this whole thing to be 1/5, right? So we force this entire thing to be 1/5. What do we need? So 3 minus what gives us 1/5. And it's kind of a fraction, right? It's kind of gross. So it's going to become 14 over 5. And that's the x value that we need in order to force this whole thing to be 1/5. So once we pick 14 over 5 for x, this whole thing will evaluate into negative 1. Because ultimately, what are we doing? If we force the inside to be 1/5, then that whole thing is negative 1. So we have 2 minus negative 1, which is positive 3. So if we somehow achieve the 14 over 5, then the y value is negative. Wait, is it negative? I'm sorry, positive 3. That's not my favorite anchoring point, but you can do it. But let me undo all that work. Okay, that's the most I can undo. Whoops. So delete that. So do we need this third point? Again, depends on teacher. But I think at this point we have we need to determine the end behaviors, which we visually represented by doing a quick sketch. Okay, so end behaviors. We do have domain restrictions. We are approaching the wall from the left-hand side. So as x approaches the wall, what is our wall? 3. So as x approaches the wall from the negative side, then the y values, g of x, then the y values explode upwards. And then as the x approaches, as we get smaller and smaller x values, and then the y values approach what? they explode downwards forever. So backwards is downwards. And then these two would be the end behavior discussion. Question is, could you explain how you would do it if you're using the B1 and what is that? 1-0 strat. Oh, okay. So that's like the most generic way you could represent the rules. So the way I did it in generating these anchor points, what I did was I directly consulted what was in here, and I forced the argument as a whole to be nice numbers. If you're building off of strictly transformation rules, like you have b comma 1/2, and then you have, what's the other number? 1-0. Then this one is for your most generic function, something like this. Log base, for example, 2. But since we're picking base 5, let's do this. So this one is based off of this one, and then this one is based off of the domain restrictions. So for this example, the b happens to be 0. But once we do shifting rules, then you need to shift these points, these anchoring points accordingly. So for example, so if we have log base 5 of, say, x, let's do x minus 3. Let's just do one shift. Let's just do that one. So if we have this one, for example, then what happens is all your x values will be affected. So this x value will be affected because this -3 is literally right next to this x inside the parenthetical. So this one will get shifted, and then this one will also get shifted. So the question is, how do they get shifted? Well, you ask yourself, in order to achieve that the one from the default standard parental function, what do I need for the x value? It needs to be 4. So this one shifts into 4. So yes, in effect, it is opposite land. So whatever value this is -3. So this one will need to be +3, and then this one needs to be +3. So this is the most very basic transformation. It's just going to be a translation. So in order to deal with more complicated situations where you have like negative modifiers, let's see for a moment. So if you have -x plus 3, for example, as what we were doing, this one has 2 transformations done on it. So when you get to the actual point, you need to apply those exact 2 transformations. And it's kind of annoying because reflections will mess up your shifts, which is why I highly encourage you factor this out. So make this into just positive 1x. So to do that, slap on the parentheses, factor out the negative. And then now you can see that there are going to be 2 transformations you have to apply to go from standard parental anchor into actual anchor point. So we have 2 transformations. We have to contend with this one, and then we have to contend with that one. And the order of operations is important. So make sure we apply it accordingly. So we can do this one first, and then we can do the reflection. Let's test to see if that's correct. So again, we wanted the result to be 1, right? But now we have this -3, but opposite land rules, right? So we want this whole thing to be 1, but we also have this negative. So first you force the 1, and then we force the negative. I think that's the order. We may have to consider changing our strat, but just off the top of my head, it'll be 4, right? But if this whole thing is 4, this becomes negative. So, you know what? Maybe we'll leave it first. Hold on. I'm trying to think here. I guess we can leave it in this form first. Let's consider leaving it like this one first, I think. Because I'm trying to just come up with a generic rule, right? Rather than just come up with individual rules. So we're doing this one, right? I guess it just depends on how you want to think about it. We want to force a 1. So how do we get this whole thing to be 1, right? What transformations do we need to apply to get this whole thing to be 1? So if we force a -2, if x is -2, I'm sorry, if x is +2, we apply the negative, and then we shift +3, right? So you could think about it like that. So what does that mean? It means that the new anchoring point will have to be based off of this 2, so +2. So if x is +2, then this whole thing evaluates into +1, and this whole thing evaluates into 0, right? And that's the actual anchoring point that we're going to get. But we're trying to come up with the rules for this one, and I think to come up with the formal rules, you need to actually factor out the negative, I believe. So let's test the hypothesis, right? So what do we need to do this? We know there's going to be a reflection, and we know that there's going to be a reduction of sorts. So how can we do this? I think we do need to consider both ideas, but I'm trying to think which order do we apply the thinking, right? So I think we need to do this negative. We need to consider the negative first, and then we need to consider this afterwards. Yeah, so it's kind of a reverse order of operations. So when we proceed forwards, it's PEMDAS. It's going to be parentheses first, and then multiplication outside parentheses afterwards. But since we're considering transformation rules, we kind of have to go backwards. So consider the negative first. So we know we have to flip the negative. So instead of having 1, we want to achieve -1 as a result, right? In order to achieve a -1 result from this one, then it needs to be 2. So we need to shift it +3. So it needs to be +3, and then we get to 2. And that now matches what we confirmed before. So yeah. So I think that's the general rule that we need to make up. So let me try to summarize that. We are starting off with something like -x + 3. If you want to formalize the rule from this one, you need to factor out the negative. And then now we go kind of backwards from outside to inside. We want a negative. So starting from the parental anchor point, which is 1, 0, this negative transformation, we transform this one into negative. So it's going to become -1. So that's applying the transformation, the reflection. And then we need to have this -3. So applying the transformation, it's going to be +3. So this is +3 to the x. So +3 gives us 2. Yeah, so that's the generalized rule. If you like to use transformation rules, some teachers will require this. Hope that makes sense. We'll go over another example after this one. So after we finish graphing this problem, we'll do something else for the x argument. I don't remember what we were talking about at this point. Okay, end behaviors. So we have the end behaviors, we have the anchoring points, and then we have the wall. So we just need to put all 3 of those together, and then we'll be good to go. I always like to put the wall first. So the wall at +3. So 1, 2, 3. And then we have 3 anchoring points at this point. So 2, 2. We have -2, 1. And we have a very awkward close to 5. Wait. Oh no, I'm sorry. This is close to 3. This is +3, yeah. So close to 3, +3. And then we'll follow the standard and the end behaviors we've already determined. As x gets closer to positive 3 from the smaller side, the y values explode upwards. So never cross the wall. And then as x approaches smaller values, the y values also get smaller. Something like that. And then we're good with the graphing, and then we're pretty much done with this one. There it is. So let's just do another one for consideration of picking anchoring points real quick. So this, I'm not going to be graphing this one, so I'm just going to be talking strictly about the picking the anchoring points. So let's list a couple of these. So no amplitude changes just yet. So we're just considering picking anchoring points. So let's do something like x minus 5, starting off with the basic one. We have this funky one right there. And let's do a goofy one where there's actually a coefficient in front of the x. So that's technically going to be a vertical compression of sorts. I'm sorry, a horizontal compression or expansion. It depends on the number. So it's only like 2x minus 1. Okay. So let's say we're trying to pick the anchoring points for f of x first. And I'm just going to do it my way first. And then we'll go pick it for a more generic. If you're trying to transform things based off of the parental anchor points, like 1, 0, or b, 0. Alright. So from my perspective, when I'm doing this type of problem, I just pick very nice numbers. So this is base 2. So I want this whole thing to be 1. So how do we force the 1? X minus 5 is equal to 1. So that's if x is equal to positive 6. So picking 6 will force the 1 input, which means this whole thing will become 0. So 2 minus 0 is 2. So the first point, anchor point, is 6, 2. So I did not get this from transformations. I just got this straight from the algebra and evaluating the log function. Anchor point number 2, we already made this whole thing into 1. The next easiest one is to force 2. So we want this whole thing to be 2. So what do we need to do? X has to be 7. So once we pick x is equal to 7, this whole thing becomes 2. Log base 2 of 2 is 1. And then 2 minus 1 is just 1. So that's how I pick my anchor points, by doing some evaluation. But if you're trying to do the, what is it called, the transformation rules. So if we know that the parental function is 1, 0, then we need to adjust it to this new scenario. And there's only one thing that has been applied. It's a minus 5. So therefore, to get to the next one, we have to do the opposite. It's plus 5 to the x value. So plus 5. That's the transformation. There's only one transformation. It's this one. And we have to do opposites. So it's positive 6. So that would give us to 0, but because we have a 2 modification on the outside, it's technically a plus 2. So this whole y value, to accommodate this other transformation that's after the fact, we'd have to pump this up plus 2. Which matches what we have before, as you can see right there. So that's if you really want to use the transformation rules. And then if you're considering the other point in question, like b, 0, this is a standard anchor point. I think b is the, what was b? It can't be this value here, because 5 minus 5 is going to give us 0. Wait, what is this one? It's if this whole thing is 1. Yeah, if this whole thing is 1, right? Oh, b comma 1, I'm sorry. B comma 1. So this one is dependent on the base of the log. I think b stands for base of the log. So in this case, it's arbitrarily 2. So this one will be 2 comma 1. So this is the standard anchor point for the standard parental function that's just log base 2 of x. We have a modification of 5, so we're going to apply the exact same transformation. So we make note the x is transformed by minus 5. So to get to the correct anchor point, it's plus 5 to the x. But then we have a plus... Oh, we do have a negative right here, right? So this whole thing, we need to flip the sign, and then we need to put plus 2, I think. We need to match this one, essentially. So that's going to be fun. All right. So 2 plus the 5 gives us to the anchor point of 7. So that is correct. And then this one, to get to the correct y value for the anchor point, what happens? Well, first we get a negative, because this negative here is one transformation. So all the y values get negative, become negative. So negative. And then we have a plus 2 right there. So it'll be plus 2. So first we change it to a negative, and then we plus 2 it. So negative of 1 is negative 1. Negative 1 plus 2 is positive 1. So there it is. Yeah. So that's how you apply the rules. Unfortunately, it's kind of annoying, because modifications in here are different from modifications out there. A negative on here is different from a negative on there, but hopefully we'll cover the situations. Let me know if you have any questions regarding this one. So we'll come back to this if need be. So moving on to this one, again, the way I like to do it, I just like to force the 1, and since the b is equal to 3, I'm going to force the 3 as well. So how do we make this entire thing equal to 1 if x is 0? If x is 0, then this whole thing collapses and becomes 0. Wait, I'm sorry. It becomes 1. It becomes 1. Wait, no, what am I saying? If x is 0, then this 1, this whole thing becomes 0. Yes, that's correct. Alright. So that's how I generate anchor point number 1. And then anchor point number 2, we're going to force the entire thing here to be equal to 3. So that forces x to be negative 2. So if x is negative 2, this whole thing becomes 3. If that whole thing is 3, then this whole thing becomes 1. So those are my 2 anchor points. But again, if we're trying to use transformation rules, what do we do? So we're going to start off with 2 parental unshifted, untransformed anchor points. So 1 comma 0. That's first one, and then second one is going to be b for base. The base is 3. So how do we get from these parental ones into transform ones, right? So 2 modifications on the x. There's a negative, and then there's a plus 1. But let's factor that out. If you factor the negative, yeah, it's much easier, honestly, to do it this way, in my opinion. But I think there are some teachers who will force this method. They're really bent on making people understand transformation rules. It is important, but it's also really tedious. Okay, so, but if we were to force the method, right, factor the negative from here. Yeah, if you want to be technical, then you do like this. But I care about efficiency, and I think this is strictly more efficient. But you can be efficient if you do it this way, but you have to internalize the rule. You have to memorize the rules, and it's kind of some hoops to jump through. There's like some... Well, we're going to see it in a moment, right? So if we factor a negative from those 2, we get to this one. So we have to consider to transform this one into that one, we need to apply these rules right here. And it's kind of annoying. And because we are in the parentheses, we need to go backwards for the transformation. So reverse PEMDAS, the negative is applied first, and then the +1 happens afterwards. So take this, apply the negative, and then +1. What do we get? We get 0. And that's not enough though, because we also have to transform the y value. So what's happening to the y value? Well, this whole thing, everything that's happening in here is only affecting the x value. So what's happening outside of the log function? There's no negative, so we don't need to flip signs. And then there's no plus or minus 3 or anything like that. So the 0 is unaffected because for this problem, no transformations on the y. So y value is kept standard. There it is. Same thing for this one right here. We are applying this transformation because once we factor the negative out, we're going to get this mapping. So because, again, we're in the parentheticals of the log function, so we reverse PEMDAS it. So negative first to this 3 becomes negative 3. Opposite land inside parenthetical is, so -1 leads to +1. So which results in -2, which agrees with what we have before, using the simpler method. But we don't have the y value, right? But remember, no transformations on the y, so it strictly carries over to be -2, 1, which is correct. So, both those points. So now, let's do this one. And in this situation, I'm not going to do the simpler method first. You know what, let me make things a little more annoying. Let's put a 1/2 in the front. Yeah, just if your teacher doesn't force the transformation, don't force the transformation. It's terrible. So let's put a 1/2 here. Now let's put a 1/3. Yeah. So if we were to formalize this, if we have to use the more formal method, which is 1, 0, transform the parental one, and then transform the other one. This is base 1, the base is 5. So let's force the method, but we need to keep track of the transformations. So what's happening to the x? There are two things happening to the x, but they don't happen in this order, even though it's PEMDAS, right? Because everything that happens in parentheses is opposite land. So we have to factor this junk out. So slap on parentheses, factor out the 2 from both terms. So we're going to get 2 parentheses x minus 1/2. So here we go. To get to the transform one, we have a ×2 modifier, but we have to do this in reverse. So divide by 2 gives us 1/2. We have a minus 1/2 inside, so we have to do the opposite, which is plus 1/2. So that's going to be 1/4. What's happening to our y values? Well, we start off with parental 0 y value. Everything that's happening outside the log affects the y value, so we only have a 1/3. But since we're outside of parentheses, this 1/3 is applied normally, so it's times 1/3. But 0 times 1/3 is still 0. And that should be one of the anchoring points. And then for the other anchor point, same thing in reverse. First, we need to divide by 2, so it becomes 5/2, I think. And then we have to add the 1/2. And that takes us to the modified input, which is 5 plus 1 is 6. 6 over 2 is 3. And we got to modify the y value, transform it as well. Again, nothing's happening to the y value except 1/3. This is outside parentheses, so it applies normally. So times 1/3. And that should be the anchoring points. And before I get to the question, let me just check real quick. So just doing the much easier way, in my opinion. So again, the easier just force this whole thing to be 1. How do we force this whole thing to become 1? Just solve it algebraically. That's if x is equal to 1. Right? Ooh, this is annoying. Okay, anyway. So if we force x to be 1, then 2 times 1 is 2. 2 minus 1 is 1. So this whole thing will evaluate to 0. And then 0 times 1... Wait a minute. This is different. The 0 times 1/3 is 0. Oh, that's interesting. Okay, well, that's why I hate this method, right? So this one's kind of dubious at this point, but let me check something real quick. So this should be the correct anchor point. Interesting. Yeah, 1, 0, right? Yeah, 1/2. So something is wrong with this method at the moment. I'm not coming up with the right mapping, but this should be the correct easy anchoring point. Yes, I would agree. 1, 0 is easy. So if you use the other method, very straightforward. And the next one, we want to force it to be equal to b, which is just 5, right? So how do we force this thing to be 5? So 5 plus 1 is 6, and then 6 divided by 2 is 3. So 3. So if this whole thing results in 5, then this whole thing evaluates to 1, and then 1 times 1/3 is 1/3. Yeah, so I will change the second one. So if it's not going to be 6, it's going to be just 3. Yeah. Because you want this whole thing to be 6. In order for this thing to be 6, the x has to be a 3. Yes. Because 6 minus 1 is 5, and 5 is optimal because it matches the base. So those are the two numbers. Oh, so this one is correct. So this mapping is correct, but the first mapping is incorrect, so I goofed up something. Yeah. Let me double check the first map. Hold on. So this mapping is correct because it worked properly with the second transformation. So again, we're dividing by the 2, and then we're adding the 1/2. Oh, I just can't do math. I'm sorry. 1/2 plus 1/2 is 1, not 1/4. I don't know how I got this 1/4. This is 1. So the transformation is correct. It's just annoying. I'd much prefer not to do it as the transformation method. Okay, so just, again, this is just talking about picking the anchoring points for purposes of graphing. This is one small component in terms of graphing the entire thing. We'll do a few more of these transformations. And checking both situations. If you have a... Yeah, exactly. Okay, so let's check it out. That's fine. I'll continue afterwards until I do like maybe 10 examples, and it should be good to go. So 3 examples of transformation situations. And don't feel obligated. Yeah, don't feel obligated to stay. It's just nice when there's someone here to actually bounce off of. Sorry, so you have f of x is equal to, let's do 2 minus 2/3 log. So we have 2 y transformations, and then we're going to have this really goofy one here. Let's do 1/2 minus x. So there's a lot of happening inside here, and there's a lot happening outside there. So that's going to be kind of annoying. All right, let's just do this one first. So let's do the more efficient way, honestly. So we want to force the 1. And since there's no number on the bottom, that means we're forcing 10, right? So invisible number is 10. So we want to force 1, and we want to force 10. So how do we get 1? So solving the algebra, then x needs to be negative 1/2. Which again, I think is a much simpler method. So if you force x, if you make x as negative 1/2, then this whole thing is forced to be 1. If that's 1, then this part right here, this is going to evaluate into 0, and then 0 times anything is 0, and then 2 minus 0 is 2. So anchor point number 1. Anchor point number 2, we're going to force this whole inside to be equal to the base, which is 10. So how do we force the whole argument to be 10, right? How do we force a 10 right here? Just do the algebra. So 1/2 minus x is equal to 10. You do the old switcheroo, plus x, minus 10 minus 10. So 10 times 2 is 20. 20 minus 1 minus 20 is negative 19. So that's what the x has to be, negative 19 over 2. So if we force x to be negative 19 over 2, then this whole thing evaluates into 10, which is perfect because base 10 and 10 argument. That means that this whole entire thing will become 1. And then we just do the rest of it. So 2 minus 2/3 of 1. What is that? That's just 4/3. So those are the two anchor points straight up if you just do the more straightforward method. But if you're forced to do the shifting rules, transformation rules, it's kind of annoying. Alright. So the x has two transformations. There's a negative and then there's a half shift. And then the y has three transformations. It has a reflection, amplitude change, and then translate plus 2. Yeah, no problem. You're welcome. You have a good one. Alright, but checking this one right here. Again, forcing the method. So we have 1, 0, and then we have b, 0, 1. What are we doing here? Base is invisible 10. So these are untransformed generic parental function. The parental function being log base 10. This one right here. But we have transformations to contend with. And like I said, just make sure we map what's going on. So in terms of what's going on right here, we factor out the negative 1. So we get this one. So there are going to be two situations. There are going to be two things happening to the x. But because we're inside parenthetical, we get weird shenanigans. Things are kind of reversed. So to transform this one, we need to divide by negative 1 and then add 1/2. So we're getting negative 1 on the flip because we're going reverse PEMDAS inside parentheticals, and then plus 1/2. So that should summarize into negative 1/2. What's happening to the y values starting from parental function 0, default parental 0? We're going to have to do these nonsense. And in this case, we're outside of parentheses. We're outside of the main function. So we apply it as normally following PEMDAS. So multiply by negative 2/3 and then add positive 2. So thankfully it's just 0. So 0 times negative 2/3 is still 0. 0 plus 2 is 2. So there it is. So our transformed anchor point is going to be negative 1, 2. It should be. Does it match? No, it doesn't. Well, oh, no, I'm sorry. Wait, am I looking at the wrong thing? Oh, yes, it does. Okay, good. So that's our using the formal transformation rules, negative 1/2, 2. It matches the first one, negative 1/2, 2. And then we just got to apply it for the second one as well. So follow the map. Remember, it's reverse mapping for the x. So divide by negative 1. I guess my notation is kind of sloppy. So divide by negative 1. And then add 1/2. So this becomes negative 10, and then negative 10 plus 1/2 is going to give us negative 19 over 2. And then, oh, this is not the right This will be 1. Again, using default parental one, this is going to be base b, which is base 10, comma 1. And we just need to transform that one. So we need to use the y transformation on that one, which is summarized by those two. So times negative 1/2, negative 2/3. So times negative 2/3. And then plus 2. So times negative 2/3 is negative 2/3, and then plus 2 is plus 6 over 3, which is positive 4/3. And there we go. And that will match what we have from before. So yes, it looks good to go. Again, this is just good for generating anchoring points. Let's do 3 more examples and we'll get to graphing. Suppose we have g of x. G of x is equal to, I don't know, let's make things up, right? We'll do log base of 4. And we're going to do 2x minus 1. Plus 5. So multiple transformations to contend with if you want to think about it like that. But let's do it the more straightforward way first, and we'll check afterwards. So this is base 4. And honestly, it's always going to be the same numbers we're going to try to force if you only need 2 points. So we're going to force the 1, and then we're going to force match the base, which is just 4. And then we just set up the algebra twice. So we're going to force 2x minus 1. First to be equal to 1, and then we're going to force it to be equal to 4. So to force the 1, it's going to be plus 1, which is 2. X is equal to 1. So if x is 1, then this whole thing becomes 1. The argument becomes 1. And once the argument is 1, we're evaluating log base 4 of 1, which is just 0. 0 times 3 is 0. 0 plus 5 is 5. So that means our first anchor point is 1, 5. And then next up, we're going to force the 4 now. Let's do it. In order to force the 4, 2x minus 1 is equal to 4. So plus 1 is 5. 5 divided by 2 is 5/2. So x needs to be 5/2 to force the 4. So once this whole thing, once we force the 4, log base 4 of 4 is just 1. So 1 times 3 is 3, and then 3 plus 5 is 8. So that's the y coordinate for the anchor point, and we have generated the 2 anchor points using what I prefer to use. But using the parental method, 1, 0, b, 1. What's b? B is the base, which is 4. So to get the anchor points using transformation method, you got to map out what's happening to the x values inside parentheses. Factor out coefficients always. So 2 times x minus 1/2. And we're going in reverse order because shenanigans are happening inside parentheticals. So reverse PEMDAS in a sense. So we have to first divide by 2, because that's inverse of times 2. Or you can think about it as times 1/2. It doesn't matter. So divide by 2 or times 1/2, equivalent, same thing. So times 1/2 first, and then plus 1/2. So this one times 1/2 is 1/2. 1/2 plus 1/2 is 1. What's happening to our y values? Well, pay attention to what's happening outside of the log function. And we could proceed in order because we're outside of the input. So times 3 first and then plus 5 second. So times 3 first and then plus 5 second. 0 times 3 is 0. 0 plus 5 is 5. So 1 bit. What do you know? It matches. And we're going to apply the same mapping to those two. So the x value and the y value. So what's happening to the x value? Times 1/2, which is 2. 2 plus 1/2 is going to be 5/2. Now deal with the y value. So y times 3 is 3. 3 plus 5 is 8. It should match up, right? There you go. Looks good. Alright, sounds good. And then we're going to do one more for the road. What shall we do? We'll pick log base, go back to 2. So something disgusting like that, right? Alright. So let's do the more convoluted transformation strategy, and then we'll reconcile it with the easier strat. And then to do that, we just need to figure out what's happening to the x value right here. What's happening? Let's start with the parental anchor points first. 1, 0, and then base number, which is base 2, comma 1. So those are parental. And what's happening to this one? Well, factor out the negative 1/2. And then we're going to get positive x, and then factor out the negative 1/2, so it'll be minus 2. So in terms of reverse mappage, what's happening to the x transformation? First, multiply by the inverse, so times negative 2 to undo this one. And then, comma, opposite of that is plus 2. So to get to the transformed parental anchor point, starting from this one, it's going to be times negative 2, which is negative 2. Negative 2 plus 2 is 0. And there it is. And what's happening to the y ones? Y transformations are all outside of the log. So times negative 2 plus 3, following PEMDAS. So times negative 2 plus 3. In terms of the mapping. So the y values get the y transformation. So 0 times negative 2 is 0, and then 0 plus 3 is positive 3, which takes us to this one. So finish with that. And now we just need to transform the other points. So the y, what's happening to the x? It's times negative 2 first, which is negative 4. And then negative 4 plus 2 is negative 2. What's happening to the y values? Y transformation, so times negative 2 first is negative 2. Negative 2 plus 3 is positive 1. So those ones should be the transformed anchoring points. But let's do the simple method. Alright, we want to force the 1 and we want to force the 2. So how do we make this entire thing into 1? Do the algebra. So we'll move this to the other side and we'll subtract 1 from both sides. So we're going to get minus 1 minus 1. And then divide by negative 2. X is equal to 0. So if we force this entire thing to be 1, then this whole thing becomes 0. 0 times negative 2 is 0, and then 0 plus 3 is 3. So thus do we get the first anchor point, which should match. There it is. And then next up, we are going to get the second anchor point. Second one easiest one is to force 2, so we're going to force this inside to be 2. Just do the algebra. So -1, divide by -2, divide by -2. So x is going to be -2. So if we force the input as a whole to be 2, then this whole thing right here becomes 1, and then 1 times -2 is -2 plus 3 is +1. Does it match up? Yes, it does, and we're good to go. Alright. Which means we could go back to graphing the situations. So we have f of x is equal to what? Let's do 3 minus... No amplitude changes just yet. But I feel like now that we've talked about the amplitudes, we could just talk about amplitude change. So let's do a 1/2 here. And let's pick base 2. So easy transformation on just the x is just going to be a horizontal shift 3 spaces to the right. So here we go. So we're going to do standard situations, standard procedures, try to have some sort of semblance of order. The more you go in your own order, then the more used to it you become. But if you want to be more flexible, do different orders. Domain issues. We have to force this one to be greater than 0. So x minus 3. The argument as a whole must be greater than 0. So x is greater than 3. Range is boring, it's just all real numbers. And from this domain restriction, x can't be 3, so x is 3 must be the wall for the VA. Now gathering the n behaviors, make sure you keep track of the transformations. We have a positive x, so x is non-reflected, but the negative is outside the log function. So we have one of those reflections across the horizontal. So this type of reflection. So what does that mean for us? This is the standard parental function. We are going to reflect it across because this affects outside the log function, so that's on the y values. So we're going to get something like this. Again, the x is positive, so we don't have this reflection. So from these ones, we will generate the n behavior results. So as x gets bigger and bigger and bigger, and the y values get smaller and smaller. So y approaches -infinity. F of x. Alright, so that's that one, and then as x approaches the wall, what's the wall? That's the wall. And we're approaching the wall from this location, so from the positive side, from the plus direction. What's happening to our y trends? The y explodes upwards. And thus we have the n behaviors. Now we're going to pick the anchor points. So picking the anchoring points, again I'm going to do my strat, standard strat. We're going to force the 1, and we're going to force the base 2. So how do we force the 1 as a whole? It needs to be +4. And once we force this one to be 1, this whole thing becomes 0. Anything times 0 is 0, and then +3 is 3. So anchor point number 1. Anchor point number 2. We're going to force this whole entire argument to be equal to the base, which is 2. How do we force 2? Fx is 5. And then once we force this entire thing to be 2, then log base 2 of 2 is 1. And this is just going to be minus 1/2. So 3 minus 1/2 is going to give us 5/2. So now we have all the ingredients for the graphing. But just as a side note, if we're doing transformation situations, then you could just ignore this on the VOD, skip this on the VOD. But again, if we're just doing transformation, make note of the x transformation. We just have a minus 3. So opposite land, it's plus 3. But let's write the anchor points first. So for the parental function, anchor points are 1, 0, and b, comma, 1. But the b one is just base 2. So x transformations first. So for the x transformation, it's going to be minus 3, but it's opposite, so it's plus 3 only. For the y transformation, we have two things. We have a negative. We have three things. We have a negative, we have a 1/2, and then we have a 3. But again, we're outside of the parentheticals, so we apply them according to PEMDAS. So times negative 1/2, and then plus 3. So let's get to applying. So apply the x transformation to x. So 1 plus 3 is 4. Apply the y transformation. Times that one is still 0, and then plus 3 is positive 3. Apply the x transformation, plus 3. Apply the y transformation, it's going to be negative 1/2 plus 3, which is 5/2. So same thing. So conceptually, it actually is the same thing, but this is just a more formalized way of doing things. Because sitting there and evaluating it is the exact same principle as this one. Okay. And now we're back to the graphing. I always like to put the wall first. Positive 3. 1, 2, 3. We have 2 anchor points at the moment. We have 4, 3. That's past the wall, right? So this way. 4. And we have positive 3. Anchor point number 1 is done, and anchor point number 2 is 5 and 5/2. This is 4, so this is 5. What is this? That's 2.5, right? So it's below the 3. So 1, 2, 3. So this is half. And then 2 anchor points are done. Now we just have to reconcile the end behaviors. As x gets bigger, y gets smaller. So after this point, as x gets bigger, y gets smaller. As x approaches the wall from right-hand approach, because it's plus, the y's explodes upwards. So as we get closer to the wall, the y values explode upwards. And then, mind the gap. We're good to go. That's the graph. I'm going to take a short break right here. I'm going to just take a quick sip of water. Alright, now we're moving on to g of x. Hold on, let me text my roommate real quick. Alright, so just making up the problem. Let's say we have just negative 1/3 and then times log. We picked a base 2 last time, so let's pick base 3 this time. And then we're going to do a slightly annoying 2 minus 3 times x. keep track of the transformations, we have what's happening to the x. There's a flip, there is a times 3, and then there's a modification. This is not the true modification. Always factor to get the true modification. And then affecting the y, we have a reflection, and we have a vertical compression. So that's the quick survey. Let's get to figuring out domain and range nonsense. Range is boring, all real numbers. Alright. The domain, just force this one to be greater than 0, because we can't have 0 or negative arguments as a whole. Greater than 0, plus 3x to both sides, just to avoid negative shenanigans, and then divide by 3, divide by 3. X is less than 2/3. And from that, we can directly generate the vertical asymptote. Just steal that same number, and that's the wall. This x is not this x, keep in mind. Alright. There's that. Let's get the, what is it called, end behaviors. So we have two transformations. We have a negative on the x, and we have a negative outside of the log. So we have two flips to contend with. So do a flip. So you make this one do a flip. That's this reflection across the horizontal. And then we do another flip. So we end with something like this against the wall. Alright. So we can summarize that using the end behaviors. So as x approaches the wall, what is the wall? 2/3. How are we approaching the wall from the negative side? What happens to the y values? The y values explode upwards against the wall. But don't call it y. Call it g of x. You might be required to put plus infinity. I'm just going to put infinity. And what happens when the x values are shrinking? The y values are going downwards forever. As x gets smaller, then the y values, they also get smaller. So we have the end behaviors, we have the asymptote, we just need the anchor points. Alright. We want to force the 1, and we want to force the 3. So, how do we force the 1, right? It needs to be 2/3. So this is 2/3, 2/3. No, I'm sorry, 1/3, 1/3, 1/3. So this is 1/3. And this is going to be -1, and then 2 minus 1 is 1. So yes. And then once we force this whole thing to be 0, 0 times 0 times negative 1/3 is 0. Not too interesting for that one. And then number 2, we want to force this one to be base 3. That means that this whole thing needs to be negative 1, which means it needs to be negative 1/3. You could verify that algebraically if you wish. So once we force this whole entire thing to be 3, then this whole factor becomes 1. 1 times negative 1/3 is negative 1/3. So we have all the ingredients, and behaviors, anchor points, asymptote. We can get to graphing. But again, just for the sake of the people who wish to go over transformations, let's look at that real quick. So VOD watchers, skip this part. 1, 0, base is 3. This is kind of annoying, right? So we need to figure out what is being applied, what things are being applied to our x. So factor out the negative 3. So we basically have three transformations. We have this thing, we have this thing, and then we have this thing. But you can kind of smash these two together. So go in reverse order. What's the transformation for the x's? First times reciprocal, so times negative 1/3. And then opposite land plus 2/3. That's the x mapping. X rules right here. Let's get to the y rules. What's happening to our y's? Well, only one thing, or technically two if you like it that way. There's a flip, and then there's a times 1/3. So smash together times negative 1/3. That's the y transformation rule, and we'll just apply both of them to x value, y value. So times negative 1/3 is negative 1/3 plus 2/3 is positive 1/3. And then transform the y one, it's still going to be 0. What's the rule for the x? For 3 times negative 1/3, which is negative 1. And then plus this one is negative 1/3. Apply the y transformation, just times negative 1/3. And thankfully they match up, so that's good. Alright, we can get back to business. Get to graphing. I always prefer to do the wall first. So 2/3, this is going to be positive 1. This is 1/3, 2/3, 3/3. 2/3 is the wall. That is the vertical asymptote. X is equal to, the wall is 2/3. Kind of awful anchor points, honestly. 1/3, 0. Negative 1/3, negative 1/3. Let us map the end behaviors. So as we get closer to the wall from the left-hand side, y values explode upwards. Alright, this is awful. And then as x approaches, as x gets smaller and smaller, the y values correspondingly get smaller as well. So as x gets smaller, y values get smaller. And then just beautify this. And then we're done. Alright, let's, what else can we do? We could do natural log. Let's do more funky numbers, right? Natural log. We got the domain and then we got the range. Range is boring, all real numbers for log functions. Domain restrictions, just force it to be greater than 0 as a whole. Plus 3 divided by 2 is 3/2. X is greater than 3/2. Alright. And from that, we could get the vertical asymptote directly. Steal this number. This x is not this x. All right. And behaviors, keep track of the signs. This x here is still positive. Out here is still positive, so no flip shenanigans. So we are standard, whoops, not that one. We're standard parental function. So concave down type of situation. I can't say my words anymore. So we have 3/2 as the wall. So that's the parental behavior. And the behavior carries over to this one. So as x gets bigger, y gets bigger. As x approaches positive infinity, then the y value also approaches g of x. G of x also approaches positive infinity. As x approaches the wall, which is 3/2, how are we approaching the wall? From the positive side, so it's going to be plus. Then the y values explode downwards. So we have the end behaviors down. Now we just need to grab the anchor points. Now this is a little funny. It's actually kind of annoying. Alright, so how do we get the anchor points? We'll force the 1 first. How do we force 1? If this is 4 minus 3, which is 1, so x needs to be 2. And once we force this whole thing to be 1, this one collapses and becomes 0. 0 plus 1 is 1. Now here's the sucky part. What's the base? It's base e, which is an irrational number. How do we force this to be an irrational number? Well, like I said, it's going to be awful. So just do the math. We're going to force the inside to be an irrational e value. So plus 3, divide by 2, divide by 2. That's not a very nice number. So that's the exact value. But if you recall, the e value is approximately 2.72. So this one plus 3 is like 5.27-ish divided by 2. So that one is approximately, what is that? 2.86-ish. Not the nicest. But anyway, but what's more importantly, if we force this whole thing to become e, log base e of e is just 1. 1 times 2 is 2, and then 2 plus 1 is 3. So this is the exact anchor point. This is just helpful for our graphing. So we have all the ingredients that we need. Again, VOD watchers, you could skip this part if you wish, as you should, but just applying transformation rules. So parental anchor points for this function, 1, 0, and then also e, 1. What x transformations do we have? We have this one. So, make sure you factor out the 2 from those two terms. So for x transformation rules, we have times 1/2. Because we got to do the inverse. And then inverse of that is plus 3/2. And again, reverse PEMDAS order because we are in parenthetical. Alright, and then the y transformation, it's just times 2 plus 1 in that order. What was it? Plus 1. Alright, which means we can transform this one from parental anchor points into actual anchor points. So times 1/2 is 1/2. 1/2 plus 3/2 is 4/2, which is 2. Now transform the y. There it is. Transform the x value according to x mapping. So e times 1/2 is e over 2, and then e over 2 plus this one is e plus 3 over 2. Transform the y value times 2 plus 1. And yes, they match up. Perfect. Okay. Back to main business. Gotta put the wall. So we have +1, +2. Hash mark, sub hash marks. And the wall is located at 3.5. Wait, why did I do 3s? Whoops. Subdivision in half. So 3.5 is where the wall is located, so that's 1 and 1/2. So right here. So vertical asymptote, the wall is at 3/2. We have 2 anchor points chosen. We have 2, 1, and then this nastiness. So 2, 1. Again, this one is approximately 2.86, so it's below 3. So this is 2.5, this is 3, so somewhere here-ish. That's where the x value is located, like here-ish. And then we have +3. So that's like way up. Wait. Let's goof up. Oh, something's weird here. Hold on for a moment. Oh, I'm sorry. I put the one behind the vertical asymptote. Whoops. That's what I get. This one is x value 1, where we're looking for x value 2. So let me delete this one. Okay. Let me start it over again, putting the anchor points. The anchor point number 1 is at 2, 1. So this is not 2, that's 1. So this is 2, and then 1. Let me put the y-axis as well. 3, 2, 1, 1. Alright, so 2, 1. We're to the right of the wall. And the next one is almost 3. It's like 2.8, 3. So 2.8-ish, 3. And then we're not deviating from the parental function n behaviors. So as x increases, y increases. That looks kind of funny. And then as x approaches the wall from the right hand side, y values explode downwards. And just bridge the gap. Unfortunately, kind of crossed the box, but that's okay. So, well, there it is. We should be good to go for this problem. I'm actually going to do one more because I've been streaming for like 3 hours. And we'll conclude it. Alright, one more problem. So we have h of x is equal to, let's, what do we pick? Let's do log base 5. Let's do log base 6. we'll just maximize the annoyance. So we have amplitude change, we have reflection, we have shift up, we have what is that? Horizontal compression, and then we have shift up, and we have reflection. So fun times all around. Let's get to it. So domain, range, restrictions, stuff, standard procedures. Domain, range, this is just a log function, so the range is just all real numbers. Domain is slightly more interesting. Argument as a whole, always greater than 0. I hate dealing with negative shenanigans, so plus x, plus 3x, plus 3x. So x is going to be less than 1/3. And then from here, we could just rip off the vertical asymptote. 1/3. What's happening with the end behaviors? Well, we have a negative here and negative there. So we have 2 reflections. So this is the parental function template up against the wall. So all we got to do is do a flip. Do a flip. So we are this one. So there's the wall. And up against the wall like this. So from there, let's state out the end behaviors. So as x approaches, we can't approach positive infinity because we're approaching the wall. So as we approach the wall, from the smaller side, from the negative direction, it's going to be like that. Then the y value, or h of x, explodes upwards. And then as x gets smaller and smaller, the y values also get smaller. Negative infinity, larger sized negative values, and then h of x also approaches large sized negative values. So end behavior is right here. And we'll be a little British right here. With the U. The funny U. Alright. And then we just need to get the anchor points. This is base 6. So we want to get 1. We want to force the 6. So do the 1 first. So minus 1 minus 1. So x is equal to 0. If we force this whole thing to be equal to 1, then this whole thing becomes 0. 0 times anything is 0. Discrete values. And then 3 minus 0 is 3. Anchor point number 1. Anchor point number 2, we're going to force the entire inside to be positive 6. So once we force, well, how do we force positive 6 first? So minus 1 minus 1, divide by negative 3, divide by negative 3. So if we force this thing to be negative 6, this whole thing becomes positive 1. Positive 1 times negative 1/5, so 3 minus 1/5. That is equal to 3 times 5 is 15. 15 minus 1 is 14. And those two are their anchoring points. So at this stage, if you wish, you could just jump straight to graphing the graph. We already have the wall, we have the end behaviors, and then we have the anchor points. So that should be good enough to get to the graphing. So same things as usual. I'm just going to do the transformations. So VOD watchers, you can skip. So what are the transformations for the x? The x transformations are, slap in the parentheses, factor out -3. What are the anchor points for the parental log base 6? 1, 0, and then, what is it? Base number is 6. These are the x transformations. So times inverse first. Or, I guess technically it's not inverse. But deal with the negative and deal with the inverse of the 3, which is 1/3. Opposite land inside parentheticals, so plus 1/3. That's the x transformation. Y transformation times -1/5 plus 3. Alright, here we go. So change the 1 by doing this. So times 1/3 is -1/3 plus 1/3 is 0. Same thing. Now transform the y value. So 0 times that one is 0. 0 plus 3 is 3. Is that correct? Yes. And next transform this other anchor point. X first. So 6 times -1/3 is -2. And then -2 plus that one is 6. -6 plus 1 is 5. So -5/3. Transform the y value using the y map. So times -1/5 and then plus 3 is positive 14 over 5. Yep, good to go. And now back to the main task. Actually, I'm going to lean it more towards this side, since we already know we're moving away from the wall to the left. What kind of nasty values are we dealing with? 3s and 1/3 and 5ths. Okay, that's kind of annoying. So -1. So 1/3 for the x-axis. And then 5ths for the y-axis. We're basically not going above 3, so let's just put, well, we need more space. Alright, so the y-axis will be a little inconsistent since my hash marks are off. So this is +1, +2. We need to hit 3, right? Okay, well. So this is 1. It's 2. That's a 3. We're going by 5ths because of this nonsense right there. But it just needs to be past 2. So 1, 2, 3, 4, 5. Let's put on the wall at 1/3. Oh, wait a minute. Oh my goodness. Okay, not a big deal. So unfortunately I kind of went off. Let me do this again. positive 1, 1/3, 2/3. Okay, there we go. So we have the vertical asymptote at 1/3. It's kind of crooked. So vertical asymptote, x is equal to... Oh, I put it at 1. Oh my goodness. Hold on. It's supposed to be at 1/3. I don't know why I put it at 1. So this is 1/3. So vertical asymptote, x is equal to 1/3. That's the wall. And then we have two anchoring points. Remember, from the parental function shifting analysis, we determined that we're to the left of the wall, so these points should lie to the left of the wall. So 0, 3, 0, 3. Yep, it's to the left of the wall. And then we have negative 5/3, which is 1 and negative 2/3 right here. And almost 3. So 1 hash mark below 3. So here's 3. We're 1 hash mark below it. So here-ish. We have the anchoring points, and now let's just reconcile those with the end behaviors. So as we approach the wall from the negative side, y values explode upwards. Well, this is really annoying. Well, something like that, I hope. As x approaches negative infinity, y values approach negative infinity as well. So as x approaches negative infinity, y values approach negative infinity. And bridge the gap. That's too sharp. Okay, well, just capture the main idea. I can't do it anymore. Okay, something like this, right? The important thing is we get the right end behaviors, as we've already noted before. We can't cross this wall, and we had two reflections. This one was reflected like that, and then reflected like that. So this graph should be good to go. And I'm going to call it because I'm getting pretty tired. I haven't eaten dinner yet. So it's time to eat dinner. And then I'll see you another time. And then you have a good one.